Welcome, everyone. So tonight we will be talking about greenhouse gases. When we finished last week's seminar, we had looked at how to incorporate the greenhouse effect into a model of the Earth's climate. And so now we are going to look at what is the greenhouse effect exactly, and how is it created by some of the gases we have in our atmosphere. Recall, in our climate model with the one-layer pane of glass, we included the greenhouse effect as a pane of glass that absorbed infrared radiation and re-emitted it at random angles so that effectively half of it went up out into space and the other half went back down to the Earth. And even though this model wasn't perfect, it suggests a definition for greenhouse gas. That a greenhouse gas is a gas that absorbs and re-emits infrared radiation. So at this point, let's remind ourselves what exactly is infrared radiation. You might remember that there is an electromagnetic spectrum. There is a whole range of possible wavelengths of light. You can also describe this spectrum in terms of the frequencies of light. But I'm going to try to stick to wavelength for this evening. Right? Every ray of light has wave properties. And one of those wave properties is having a wavelength, which is you could think of this as the distance from one peak of the wave to the next. And so what humans have done, according to our needs in terms of how we use these waves, but also in terms of how we observe these waves interacting with matter, is we have divided the electromagnetic spectrum into regions according to the wavelength, or if you like, the frequency. But I said I was going to stick to wavelength. So we have gamma rays, highly energetic, don't encounter these much on Earth. X-rays, which we mostly encounter in a medical observation setting. Ultraviolet, which is present to some extent just from sunlight, although our atmosphere does a pretty good job of blocking most of the ultraviolet light, or at least the higher energy ultraviolet light. The visible light, which is everything we can see, right? So here you really start to realize that these regions are defined by us and our perceptions. We drew the lines at the edges of the visible range based on what our eyes can perceive. Other creatures on this planet can see into what we call the ultraviolet or the infrared. Speaking of infrared, that is the next one down, right? Abbreviated here IR for infrared. And then at some point we drew a line down here and said everything else is wait a minute, there should be microwaves on this picture. How did I miss that? So somewhere in there are microwaves as well as radio waves. But that's not important right now, right? So infrared light is what we're going to be focusing on. But now the radiation absorbed by the Earth from the sun is mostly in the visible region. The sun's spectrum of light that it emits, it doesn't emit everything, right? What the sun emits is mostly visible light with some ultraviolet and some infrared in there, but mostly visible light. This comes in through the atmosphere, it is absorbed by the atmosphere and by the Earth's surface, and then it is re-emitted by the atmosphere and the Earth's surface, usually in the infrared wavelength range. So this is the infrared radiation I'm talking about when I say the greenhouse effect warms the planet, right? The atmosphere re-emits infrared radiation back towards the surface of the Earth, and that is the greenhouse effect. So we need to talk about stuff that absorbs and emits infrared radiation. And there is an amazing simulation that is going to allow us to explore this for ourselves. So I'm going to take this simulation link and I'm going to put it into the Zoom chat because I want you, yes, you, to try this. Okay. Our prediction is that a greenhouse gas will absorb and emit infrared light. When you open this link, oh, I should probably actually paste it. When you open this link, it will show you different gas molecules you can put in front of an infrared flashlight, right? So I want you, again, yes, you, right, sitting here at home watching this, to open this simulation and try a gas molecule, right? And I'm going to go over here to a table. It's a very simple table. Greenhouse gas or not a greenhouse gas, right? So when you guys have a result to report, let me know, right? You'll know if one of these gas molecules absorbs and re-emits infrared radiation if, when you see the little red colored infrared light hit it, it wiggles and then re-emits it at a random angle. Welcome. If you're just joining us, we are testing some gases to find out if they absorb and emit infrared radiation. Of course, some of these in the list that's in the simulation, you might already know if they're a greenhouse gas or not. So let's see if we can't, Deborah?
Did you say if it goes off of the funny angle that means it is or is not a greenhouse gas?
Is a greenhouse.
That means it is a greenhouse gas.
Yes, is a greenhouse gas. That's the idea.
Okay, trying again.
So I'll change my screen share as well to open up to the simulation. This thing also makes really hilarious sounds.
Okay, it seems like nitrogen dioxide is a greenhouse gas.
Nitrogen dioxide. Let's test it. Okay, so here we've got nitrogen dioxide. And I press the button. And sometimes it doesn't always happen, right? Oh, look. It does like a wub, 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 right? That little wiggle dance it's doing means it absorbed the light. And then shortly after, I see the light fly off in another direction. Enough of that, right? So nitrogen dioxide is indeed a greenhouse gas. Let's go back to the slide and write that down. It's not science if you don't write it down. Nitrogen dioxide. Not to be confused with nitrous oxide, which is that stuff they used to give you at the dentist office. Anyone got another one they know?
Ozone is a greenhouse gas.
What was that gas?
Ozone.
Ozone absolutely is a greenhouse gas. Ozone, right? Oxygen, oxygen 3. I'll put the molecular formulas in here as well, right? Ozone being 3 oxygen molecules, nitrogen dioxide, NO2, right? Nitrous oxide, by the way, is N2O, right? So you know it's not the same molecule. So we got 2 so far, nitrogen dioxide and ozone. The simulation also allows us to test carbon monoxide, diatomic nitrogen and oxygen,
Methane.
carbon dioxide. Sorry, shout it out again.
Methane.
Methane is absolutely a greenhouse gas, right? Methane.
Water.
Methane. Water. Good old-fashioned water, H2O, right? Methane, CH4, a carbon and 4 hydrogens, right? So there's our methane and our water.
Nitrogen is not a greenhouse gas.
Correct. N2, diatomic nitrogen. N2 is not a greenhouse gas. It will not interact with the infrared radiation no matter how hard you try. We're getting near the end of the list now. Just a couple more. Let's see. What haven't we tried yet? Let me go back to my simulation.
Somebody say carbon dioxide.
CO2.
Of course, CO2, right? I'll do this one because this is the big one, right? This is CO2. Look at that, right? Immediately absorbing and re-emitting infrared radiation. So CO2 is definitely a greenhouse gas. What about oxygen? What do we think about O2? Michael's shaking his head no. Let's try it. Whole lot of nothing, right? So oxygen is not, O2 oxygen is not a greenhouse gas. I think that's all of them. I think we got the list now. So let's go back to my slide.
Carbon monoxide also.
Oh, and we missed carbon monoxide, which is, yes, a greenhouse gas. So let's see.
How
Carbon monoxide. No subscript here, just CO. Whoops. CO, right? Oxygen, O2, and of course, carbon dioxide. Right.
Fluorocarbons.
Now, chlorofluorocarbons did not come up when I recently checked again what was considered a greenhouse gas. Certainly, if they are, then now that you mention it, I have reason to believe that they are, but I believe that they are not responsible for a large warming effect. They're certainly not one of the heavy hitters. They're not even one of the minor league hitters. And we'll talk about.
Isn't their biggest effect that they knock the O3 into O2, so it reduces the ozone layer?
Correct. The big problem with the chlorofluorocarbons was that they are damaging to the ozone layer, and we'll talk more about ozone in a little bit. Here is a slightly more complete table that I created, where I have the name of the, well, I guess I should say greenhouse, gas, right? So I have the name of the gas. Here, let's just change that to name of gas. Formula, right? Nitrogen, oxygen, carbon dioxide, water. You notice I've ordered these more or less in the order of their composition of Earth's atmosphere. So nitrogen, almost 80% of Earth's atmosphere by volume. Oxygen, no slouch at nearly 21%. Carbon dioxide, 0.0407%. There are things I'm not listing here. I'm not listing argon, which would be the third thing on the list, right? We're skipping over some stuff that is not relevant to our discussion of greenhouse gases. Water vapor is usually about 0 to 3% of the total atmospheric volume, but it's so very variable depending on where you are and what the weather is and what the season is. It can go all the way from 0 to 3%. And so we usually don't, when you ask, hey, internet, what is the atmosphere made of? Nobody mentions the water. We talk about the dry air percentage, which is to say without the water. And then the other ones we've talked about here, from ozone down to nitrogen dioxide, I'm not even going to bother listing a percentage. These are trace elements in the Earth's atmosphere, but I did look up how many parts per million or parts per billion these gases are in the atmosphere. They have a very small presence, and yet, as we'll see, at least in the case of methane and ozone, they nevertheless can have a large effect on the Earth's atmosphere. And so notice something about this list. This is why I love this simulation, right? Almost all of these are greenhouse gases. The only exceptions are nitrogen and oxygen. And it's a really good thing for us that nitrogen and oxygen are not greenhouse gases, because together they make up 99% of the Earth's atmosphere. So we are very fortunate that the things which are greenhouse gases together make up less than 0.5% of the atmosphere. If O2 was somehow a greenhouse gas, life on this planet would be very different. Michael.
My question is, if water, you're saying it's between 0 and 3, but presumably the average is quite a bit above 0.
I suppose so.
And since CO2 is basically 400 parts per million,
Mm-hmm.
I assume the water vapor in the atmosphere is quite a bit higher than the CO2. So in other words,
Again, it
it
depends
should
on where you
dwarf
are.
the CO2.
What was that last part?
it should dwarf the CO2 content.
In many cases, it does. And we'll be asking a question about that later. All right. So let's try to put some things together here. If we put some puzzle pieces together, like good scientists, we will arrive at a very, very important conclusion. So, what do of all the gases we listed as greenhouse gas molecules, what do they all have in common? Anybody have a guess? Let's go back and look at the list again. All the ones I listed as greenhouse gases, what do they all have in common? There's a number of right answers to this question.
Oxygen.
Okay, because they all have oxygen in common, except methane. Methane doesn't have oxygen. So it's a good theory, but I found a counterexample. So it's not oxygen. There's something else they all have in common. I'll give you a hint. Start counting atoms.
An odd number of atoms.
They have an odd number of atoms, right? So let's see. This one has 3 atoms.
Not
This
carbon
one has
monoxide.
3 atoms. Oh, carbon monoxide has 2 atoms. So hang on. That's good enough to write down. That's good enough to write down. They all have 3 or more atoms, except carbon monoxide. So maybe we can come up with a reason why that's okay. What do the non-greenhouse gas molecules have in common? So again, the only ones there were N2 and O2. Not a lot of data to go on, but what do those 2 molecules have in common? What's similar about those 2 things?
They're not compounds.
That's right. They're the same atom, right? They are homogeneous molecules, right?
But so is O3.
Okay, fair enough. So they are made of the same kind of atom. Note, so is the greenhouse gas of O3. So maybe if we put these together, we've got one thing where we say, okay, they've got to have 3 or more atoms, but there's an exception to that. Or another thing where we say we've got to have the same kind of atom, except there's an exception to that. But maybe if we sort of take a Venn diagram situation here and we say, okay, what differentiates a greenhouse gas from a non-greenhouse gas? I don't know what that was. Any molecule made of only 2 of the same kind of atom is not a greenhouse gas. Whereas any molecule made of 2 different kinds of atoms, 2 different elements, or of 3 or more molecules is a greenhouse gas. And this might seem like a kludge of an answer, but it's true. Go figure, right? This is one of those times where you can literally do some actual molecular classification science based on a simulation somebody made on the internet. How about that? Right? So, before I explain the underlying answer behind all of this, and I think you're going to like it, this is a good time for a historical note. There was an amateur scientist in the 1850s named Eunice Newton Foote. She conducted experiments that revealed the warming effect of carbon dioxide and water vapor on sealed containers of air. Quote, an atmosphere of that gas, CO2, would give to our Earth a high temperature. And if, as some suppose, at one period of its history the air had mixed with it a larger proportion than at present, an increased temperature must have necessarily resulted. End quote. So Eunice Newton Foote was the very first person to realize what carbon dioxide and water vapor do to the temperature of the planet. They raise it, right? Now, what I quoted here is the closest evidence I could find that Eunice Newton-Foote was talking about climate effects of these gases, of greenhouse gases. She certainly was not predicting that this was about to happen, nor was she going off of data that suggested it was already starting to happen. That fell to another scientist named John Tyndall 3 years later, who did a much more comprehensive study of the Earth's climate and was possibly, although I need to check this again, the first person to state in some terms that the Earth was being warmed by carbon dioxide at that time. But it's worth noting that Eunice Newton-Foote kind of got there first. She was also, in 1848, a member of the editorial committee for the Seneca Falls Convention and one of the signers of the convention's Declaration of Sentiments. All right, onward. What is going on with these greenhouse gases? Well, as we said, a greenhouse gas must be able to absorb and emit infrared radiation. To do so, it must be able to create an electromagnetic wave with a wavelength in the infrared range. Oh, Deborah has asked an amazing follow-up question. Did Tyndall know about Foote's work? Very likely not, because, as I said, Foote was an amateur scientist and a woman in the 19th century. So it seems very unlikely, and I don't recall reading about this. I don't think her work was spread very far and wide, and I think it was only recently rediscovered. All right, so a greenhouse gas must be able to create an electromagnetic wave with a wavelength in the infrared range. Now, electromagnetic waves of any kind are created by the motion of electric charges, protons and electrons. So I wanted to show you a visualization of that. You can you can follow the link if you like. If I guess I'd have to type it, enter it into the chat for you. Here it is. You can follow this if you like, but I'm going to change my screen share to show it to you. Okay, so this is from a website of physics simulations, and we can see that the charge in the center, right, the red dot, is radiating outward these electric field lines, which you might remember learning about in your science classes. Right, so I got these electric field lines coming out of the charge, and if I simply move the charge forward,
Sharing your screen?
is it not share? Oh, did it not
it's
share?
sharing your slideshow right now. You
Uh-oh.
have to either
I thought I had
unshare and
changed
share
it. My
again.
mistake. How about now? Let's reset. Can you all see the new animation? Great.
Yeah.
Sorry for that. I'm not sure what happened there. So if I simply move the charge in one direction, not much happens, right? However, if the charge is made to oscillate up and down, look what happens to those field lines. They take on a decidedly wavy shape, right? If I increase the speed, they wave a little faster, right? So these waves in the electric field lines are electromagnetic waves. This charge is radiating light. If I make the charge move in a circle, we get a really trippy effect. This charge is radiating quite a lot of light. Okay, so that's what's going on there. Let's go back to the slides. So, in general, if we want to focus in on infrared radiation, you not only need the movement of charge, but you need an imbalance of positive versus negative charge that moves back and forth. If I have an equal amount of positive charge and an equal amount of negative charge, and they're moving in a symmetrical fashion, that molecule will create some radiation, but it won't be infrared radiation. Most likely it'll be microwaves or radio waves. If I have more positive charge than I have negative charge, and I get that moving back and forth, well, that's asymmetrical. right? So I need some kind of asymmetry of electric charge oscillating in some way, and then this will produce and absorb infrared radiation. Let's take a look at some pictures of the molecules we classified. So here we have the ones that are made of 2 atoms. Okay, so nitrogen, N2, O2, and CO, right? Any molecule that is completely symmetrical, composed of the same atoms, right, is going to have the same amount of charge on one atom as it does on the other. And so it cannot do any kind of asymmetrical dance. I'll show you on the next, coming up, I'll show you what it can do, and it isn't asymmetrical. But carbon monoxide is made of 2 different atoms. There's going to be more charge on one atom than there is on the other. And so if carbon monoxide, if the carbon and the oxygen are sort of oscillating back and forth relative to each other, then there's an asymmetry of charge. And so carbon monoxide is a greenhouse gas. Now let's take a look at these 2 guys, because you'd think, okay, here's carbon dioxide. It's nice and symmetrical. It's got an oxygen on each side of the carbon. And water is symmetrical, right? Okay, maybe it's at an angle shape, but these are symmetrical shapes, right? Well, they can bend in more ways because they have 3 atoms. So this is where we need to look at how these molecules bend and oscillate, or as I like to say, the dancing molecules, right? So a molecule made of 2 identical atoms has only 2 dance moves. There's only 2 things it can do. It can squeeze together and stretch apart, like this, right? Or it can rotate. That's it. That's the only thing it can do. It's too simple a shape for anything more complicated than that. And neither of these dance moves change the symmetry of the molecule. And without changing the symmetry, you don't get any infrared radiation. But if we look at something that's got 3 atoms, like say carbon dioxide, well, it's got more dance moves. It can rotate just like the nitrogen. It can do the symmetrical dance, the stretching in and out just like the nitrogen, but it can also lift its arms up and down, right? And so if I'm lifting my arms up and down, there's an asymmetry to how the charge is moving. If the carbon is moving down and the oxygens are moving up, then maybe the positive charge is moving down while the negative charge is moving up, right? And so there's an asymmetry to the movement of the electric charges. Or one oxygen could come in while the other goes out, and vice versa, right? So now the carbon and one oxygen are next to each other, and the other oxygen is out over here, right? So you got the asymmetric stretch, right? So you got the dancing molecules, right? It's got enough dance moves to allow it to absorb and radiate in the infrared part of the spectrum. Okay. That was a lot. Does anybody have any questions before we go on? Okay. So, to clarify and recap, the things which are greenhouse gases are electrically asymmetric in some way. This allows them to interact with the infrared radiation and absorb and re-emit it, which traps the heat. But there's a little bit more to the story. So the absorption and emission of light by a molecule depends in detail on the wavelength. We've been saying what I've been saying so far is, does it absorb infrared radiation? Well, actually, there's many wavelengths of infrared radiation, and it depends on which wavelength you're talking about. You could be 1 nanometer of wavelength off, and the molecule will say, no thanks, I don't want that. But if you hit the wavelength bang on, it'll absorb and re-emit it. So really, we're talking about three factors here. What is the exact wavelength? Of course, there are bands of wavelengths, right? How much gas is there in the atmosphere, and which wavelength bands it absorbs, right? So the strength of each gas's contribution to climate change depends on the atmospheric concentration of the gas and which wavelengths it will absorb and therefore re-emit. So let's start to look at what's going on in this picture. We're going to add more to this picture as we go, but let's see what we've got here. Radiation transmitted by the atmosphere. Okay, so this vertical axis here is labeled spectral intensity. That's a really fancy term, spectral intensity, right? But really it just is a stand-in for how much energy are we talking about here? How much radiation energy are we talking about here? So in the red, on the left-hand side, is downgoing solar radiation, which is to say the light from the sun that arrives at the surface of the Earth, right? This is what we represented last week as 340 watts per square meter. And you notice that mostly it's coming in the visible light, with some in the ultraviolet and some in the infrared. But the large chunk of it is in the visible region of the spectrum, right? And then over here in the blue, upgoing thermal radiation, which is, of course, the radiation that the Earth is emitting from the surface. So the Earth reflects some of the energy from the sun, absorbs the rest, and re-emits it as infrared or thermal radiation. And so that's all down here on the infrared part of the spectrum. See here, it's numerically got a numerical axis of the wavelength at the bottom, right? Going from 0.2 micrometers up to 70 micrometers. Okay. And so we can sort of put this all together and look at how much of the light is going to get absorbed and re-emitted or scattered by the atmosphere. So if you look at the upper half of this image in the red and the blue, and you look at the negative space, the white space in the lower part of the image, you see that, wait a minute, if I were to take the red and blue parts of this picture and fold them down, they fit very neatly into this white space here, right? In other words, the red shape and the blue shape are what get transmitted. Everything else is gray in the lower part of the picture, and it's what gets absorbed and scattered. So, the more we absorb in the infrared, the warmer we get. That's kind of what infrared radiation is, right? It's stuff that will cause molecules like the ones we have on the surface of the Earth to vibrate faster, giving us heat energy. So we would like to know which gases are doing what here. So we can take the gray region and break it down even further. We can say, all right, where does water vapor do its absorbing? Well, water vapor absorbs a lot in the large wavelength region of the infrared, right? This is where you get like your microwave oven is sending exactly that kind of radiation into your food, because it makes the water molecules inside the food vibrate, and that heats up your food. But water vapor does not absorb so well. Hang on. Let me see if I can't. Where did I? Oh, I guess I can't do it because. Okay, we'll have to do it the other way. Right? Water vapor does not absorb so well over here. There's a region of wavelengths around 10 micrometers where the water vapor just lets the radiation pass through. And you notice this corresponds to the region of wavelengths where the atmosphere just emits a lot of the Earth just emits a lot of radiation. It just sends it right up through the atmosphere. So there are these windows where we can absorb, there are these windows of wavelength numbers where the atmosphere just lets the radiation go, because the water vapor doesn't absorb it. Neither does the carbon dioxide or the oxygen and ozone or the methane or anything else, right? There's nothing here. There's a clear path from the surface of the Earth out to space, right? But let's clear all that away. Carbon dioxide is no slouch in the neighboring wavelengths. So right at this peak where we would want to emit a bunch of radiation, there's a bunch of, it's like there's a bunch of missing radiation here, right? These curves in the pink and the blue and the black are where we should be, quote unquote, should be emitting radiation if the Earth was better at emitting radiation. But something has removed that radiation, and the answer is the culprits are the water vapor and the carbon dioxide right here, right? And they are absorbing and emitting, about 10 to 15 micrometer wavelength radiation, right? This is a logarithmic scale. So this over here is 20. That's 20, right? So in the 10 to 20 micrometer range, the water vapor and the carbon dioxide, they just eat that radiation right up. And so any radiation that the Earth tries to emit from its surface that has that wavelength, it's not going to get very far before it runs into some water in the atmosphere or some carbon dioxide in the atmosphere, and it's going to get reabsorbed and then re-emitted at a random angle. And that is what warms the planet, which we need. Remember from last time, we need the greenhouse effect. But the problem is that recently the carbon dioxide peak is becoming a little bit too big for its britches. Right? Now, you might have heard about methane. We'll talk about methane in a minute. What's it doing down all the way over there? Okay, let's start talking about some of these individual gases in a little bit more detail, and then we should be able to wrap up in time for any other questions you might have. We'll start with the little guys. Carbon monoxide and nitrogen dioxide. Consider the following questions. Why is carbon monoxide a greenhouse gas since it has only 2 atoms? Anyone remember the answer to that? Somebody asks you later, hey, wait a minute. What's going on with carbon monoxide?
Asymmetric.
It's asymmetric, right? It's got 2 different atoms, and so it's got an asymmetry of electric charge. And so when it dances, the electric charge is going back and forth, right? In an asymmetric fashion, there's more charge over here, there's more charge over there, and so it will absorb and emit in the infrared. Is nitrogen dioxide the same thing as nitrous oxide?
No.
No, they're 2 different molecules, right? I don't know about you guys. I'm a little rusty on my chemistry formulas. I remember trying to memorize these OUS endings and oxide endings and all that good stuff when I was in high school, and it's gone. But I know that nitrogen dioxide is not the same thing as nitrous oxide. Nitrogen dioxide generally comes from natural processes as well as from, agricultural. We do like fertilizer. And in particular, there's another environmental impact to nitrogen dioxide. Nitrogen dioxide impacts the formation of ozone and leads to acid rain, right? So that nitrogen, that extra nitrogen, will get distributed into the water vapor in various regions, and you get this sort of nitric acid that is raining down instead of pure water. So those are the little guys, right? Yes, they're greenhouse gases, but there's so little of them in the atmosphere that they really don't have much impact on the Earth's climate. Although it is worth pointing out that concentrations of carbon monoxide are obviously much higher in urban areas. And of course, there is the whole thing about carbon monoxide poisoning, where if there is a very high concentration of carbon monoxide in your house, that's very bad news. But that's a much more local phenomenon. All right, next we're going to talk about, let's see, next up on our list, let's go back to the concentration list. We took care of these 2 guys, the really little ones. Next up is methane. And so I want to talk about methane and the band saturation effect. Hang on, that's the wrong picture. Here we go. All right, so carbon dioxide is the poster child of greenhouse gases, and for good reason. We'll talk about carbon dioxide in a minute. But on a per molecule, pound for pound basis, methane is the more potent greenhouse gas. Why? Relative concentration. So this is what we call the band saturation effect. And the band I'm talking about is not the Rolling Stones. It is the band of wavelengths that these gases will absorb and emit. So let's go back over here. Okay. Think of this pink curve or this blue curve as the radiation we would emit if there were no greenhouse effect or if there were no atmosphere, as in our naked Earth model, right? And carbon dioxide comes along and it takes a bite out of that curve, right? And so there's this band of radiation, this band of wavelengths that carbon dioxide is stealing from what quote unquote should be emitted if we didn't have an atmosphere. But you notice that that band is all the way down to the bottom of the picture, right? It can't go any lower. Now, this doesn't mean the atmosphere is insensitive to carbon dioxide. Far from it. If we add more carbon dioxide, the problem gets worse. What happens to the carbon dioxide band instead is that it gets wider. I'm not going to talk about why that is. That's a little bit more complicated than we have time for. But notice what's going on with methane, right? Oh, you know what? I'm not actually sure this picture is reflecting it. That's unfortunate. Because if I go up from methane, I see that there's also nothing there. But in fact, the absorption of methane, because there is so much less methane in the atmosphere already, it's not taking as big a bite out of the atmospheric emissions of radiation as carbon dioxide is. I feel like I've chosen the wrong image to explain this, so I apologize if this is confusing. But suffice it to say, adding new methane is a proportionately larger effect than adding the same new amount of carbon dioxide. And that's because the band of wavelengths that the carbon dioxide absorbs radiation from is more saturated already than methane's band of wavelengths. Right? Carbon dioxide is already out there doing its thing. Right? You add 10 more molecules of carbon dioxide, so what? Right? You add 10 more molecules of methane, and it's free real estate to those new molecules. They don't have any competition yet, so they're able to be very, very effective. Notice also that methane, I don't have a picture of it here, but we'll go back to the formula. Methane, CH4, has 5 molecules. So it has even more dance moves than the carbon dioxide does. But funnily enough, it doesn't have that big of a band. Go figure. Okay.
Degrees of freedom.
Switching gears. Let's talk about ozone. Raise your hand and be honest, right? Be honest about this. Have you ever thought that the hole in the ozone layer is related to climate change? Have you ever even encountered this idea?
Yeah, I'm sure it is.
Maybe one of you has done this, right? Maybe 2 of you. What's interesting is that when I teach some of these ideas to the SAR students, a lot of them have this idea. And I'm still trying to figure out exactly why that is. But apparently it's not just an SAR thing. I've encountered some literature to the effect that it's a sort of general in the winds misconception some people have, that climate change is caused by the hole in the ozone layer. And this is not true. This is just flat out false, right? The ozone layer primarily serves to block UV light from reaching the surface, right? Again, without the ozone layer, life on this planet would be very, very different. Life would have had to evolve to the pressure of having ultraviolet radiation all the time. So there was and still is a hole in the ozone layer, and it is a remarkable feat of environmental policy that chlorofluorocarbons were emitted from our removed from our industrial processes very, very quickly. And so the hole in the ozone layer over the South Pole is healing, last I checked, according to projections. It's not closed yet, but it is on its way. And this really does not interact much with the increased presence of carbon dioxide in the atmosphere, which is the primary driver of the main climate change. Speaking of primary drivers of climate change, we saw that over here in the absorption picture, water is kicking carbon dioxide's butt. Look at all of this absorption by water vapor, all of this over here. Whereas carbon dioxide has this one little peak, right? And methane's got that one little peak. Why are we talking about carbon dioxide and methane when it seems like we should be talking about water? Why is it the climate change crisis about reducing the H2O we emit into the atmosphere? Anybody got any ideas about that one?
H2SO's been there.
That's it. Who said that?
Alan.
Dima. You're right. So in other words, the climate crisis isn't about reducing the H2O we emit because humans do not emit any new H2O, right? Sure enough, we put out a bunch of water vapor from some of our activities, but the water cycle was already there. Right. We are not really making a dent in the water cycle or really any substantive changes to the water cycle as it exists, as it has historically and geologically existed. Right. Or put another way, if you like, the cycles of this planet are much better at reabsorbing water and recirculating it than they are at doing the same thing for carbon atoms. Speaking of carbon, so we come to the big man on campus, carbon dioxide. The extraction from in-ground sources and subsequent emission of carbon dioxide by human activities is the single biggest factor in the alteration of Earth's climate over the last 2 centuries. And yet, here's an interesting fact. We as human beings move far less carbon than nature does. Far, far less. So next week's session is going to be all about the carbon cycle. What natural processes move carbon around? Where is most of the carbon? And just what are we doing to mess it up? I've given you a couple of hints on this slide, but we'll learn more about that next week. Okay. Questions?
I just wanted to add, I wrote in the chat that acid rain results from the reaction of water and nitric oxide because it forms nitric acid.
Yes, yes, I believe you are correct.
Yeah.
Questions? Michael.
I guess going back to where you were showing the concentrations in the atmosphere, even though obviously man is not necessarily changing the water cycle, the amount of water vapor in the atmosphere so far dwarfs the CO2 concentration so as to make it almost rounding error. And it's just, I guess, even though, you know, CO2 is obviously absorbing, I guess I just see water being the bigger problem, if you will, even though there's nothing you can do about it.
Right. It's an understandable question, right? As I pointed out here, water vapor is so much better at this greenhouse thing than carbon dioxide is. But really, even though I just said we don't move as much carbon as nature does, proportionately our impact on the carbon cycle is much larger than our impact on the water cycle. That's the difference.
Well, I guess what I'm saying is any random perturbations in the water cycle will dwarf whatever we're doing on the carbon side.
You might, I see where you're coming from, but it turns out the answer to that is no.
Okay.
I guess, okay, if we were to channel all of our time, energy, money, and effort and experience and expertise into putting massive heating systems that floated on the surface of the ocean such that we were evaporating just a ton of water, just the great Atlantic humidifier, right? Just running full steam, pun intended. Yeah, then we could probably have a water-based climate change problem. That's the kind of effort we've been putting into burning carbon-based fuels. See the difference? One of my more ridiculous analogies, I'll admit. Any other questions? Yes, Michael.
Got another one just going mildly off topic, which
That's
is
fine. We got time.
the extra CO2 in the atmosphere. What I personally view as the more immediate threat is the CO2 getting absorbed, frankly, by the ocean.
Oh, yeah, that's a problem too.
Carbonic acid.
Yeah.
Which then changes the pH of the ocean, which then more directly affects life on Earth in a more immediate way than any subtle changes in temperature over the course of decades is going to make a difference.
My understanding is that it's kind of, it's all one multi-headed hydra of a problem. Or I guess the way I'm thinking about it is, we're causing a bunch of extra carbon to be emitted, which all goes into the air, and then some of that goes into the water, right? As far as I know, the amount of carbon we're emitting sort of directly into the water through like liquid runoff, or solid waste that gets dumped into the ocean is very, very small compared to how many tons of carbon we're putting into the atmosphere.
Now, I was talking about atmospheric carbon dioxide reacting with ocean water to create carbonic
Right.
acid.
So then when we put it into the air, then of course the air mixes with the ocean water and we get all of those problems you described, the acidification of the oceans and the warming of the oceans. And these are major problems. And I think the general perspective on the climate crisis is that if we just stop emitting so much carbon in the first place, then we solve both of those problems. We solve what's going into the air and we solve what's going into the water. Or at least slow it down. That's just my 2 cents.
Okay.
Yeah. Anyone else got questions? Lisa, you're very welcome. Why don't we call it here? I'll see you guys next week for the carbon cycle.
Okay.
Thank you so much. This was great.
Thank you for coming.
Thank you.